All right, let's work problem 5.6. Chapter 5 is all about gases, okay? Problem reads, barometric pressure on a day is 730 millimeters of mercury. What is this reading in centimeters of water if the density of mercury is 13.6 and the density of water is 1 gram per cubic centimeter? Now let's explain this problem and how it works. I think it'll make a little bit of sense. All right, so first off, we're dealing with barometric pressure. We're using a device called a barometer. Measures atmospheric pressure. And if we were to go see what one of these devices look like in sort of a simplified form, what we'd see there'd be this dish or bowl of mercury down here at the bottom. Now, mercury is a liquid metal, right? It's like a fluid. It flows around, okay? And we'd fill up a dish with some liquid mercury. And then what we would do is we'd take a long glass tube with marks on the side, graduation marks, okay? We'd fill that tube up with liquid mercury, and then we'd invert it inside this dish, or we turn it upside down inside this dish, such that the bottom is immersed under the pool of mercury. Okay, so the liquid level of mercury might be here, right? And the outlet of the tube is down below that, okay? Now, an interesting thing would happen. Now, mercury is a pretty dense metal. It's a pretty dense material. You probably recognize that. You might think that all the mercury would just spill out into this bowl, okay? And then this tube would be empty. But that's not what happened. Some of the mercury does, in fact, kind of flow back into this bowl, okay, but not all of it. And the reason why that is because what begins to happen is when that mercury comes out of that tube, it creates a vacuum in this space, or a very low pressure environment, okay? It's essentially kind of sealed off, other than having a little bit of mercury vapor in there. But atmospheric pressure is pushing down on this surface of this open bowl of mercury. Okay, so that atmospheric pressure kind of pushes down on this and keeps that mercury suspended in this column to a certain degree. Now, depending on the weather conditions, maybe the pressure goes up or goes down, and as a result, this level rises or falls just a little bit. Okay, now what we can do to measure the atmospheric pressure, the barometric pressure, is we can measure the height of the column to the top to the bottom, and that column height, as measured in distance units, either centimeters of mercury or more commonly millimeters of mercury, that distance from this fluid level to this fluid level tells us what the barometric pressure is. If that's a higher distance or a larger distance, well, the atmospheric pressure must have increased. It's pushing harder to make that level come back up. But if the atmospheric pressure is lower, maybe that drops some. It's not pushing quite as hard, and some more of the mercury can kind of pour out into this bowl. Okay, so depending on the atmospheric pressure, that level rises or falls. Okay, so this is a pretty ingenious device for measuring pressure. Then we just have to measure the height of a column of mercury. It's used all the time around the world. Okay, now the thing is in this problem, they don't really want us to give the reading of what it is in millimeters of mercury. In fact, it's given the problem. It's on this day, it's 730 millimeters of mercury. But what they want us to project is how large that column would be if I did a hypothetical experiment. If I replaced the mercury in this tube for water. Now, there's nothing that says I can't do that. I can put any fluid in this tube that I want. Just so happens mercury is kind of convenient for a reason that we'll discuss here in a little bit, okay? But I could put water in the tube. I could make this whole thing water. I could have a dish of water in my tube, invert it. No big deal, okay? But the thing is that there's going to be a kind of a complication if I were to use water. Okay, and let's talk about what that complication would be in a little bit more detail. And the trick is going to be finding what the column of water would be if I used water instead of mercury. Now, fortunately, there's a pretty easy way to figure out, using this equation, what that column length would be if I used water instead of mercury. Okay? H's here are the heights for the water column and the mercury column, and D's are our density. It turns out that this density ratio helps define the ratio between the two different materials, here water and mercury. And that makes a little bit of sense because on any particular day the atmosphere is going to be pushing with so much force, right? And it's going to have to be pushing against a certain mass of mercury in this tube or a certain mass of water in this tube. And it's going to have differential ability to do that because mercury and water have different densities, okay? Now, if I want to figure out then what the column of water would measure, if I was to actually measure it, I can use this equation. Now my unknown variable here is my H2O. That's my height of my liquid water column. In my denominator, I would have my height of the mercury column. Now I'm told in the problem that it's 730 millimeters of mercury. Okay, but I'm going to do one thing here right off the bat. Notice that our answer is supposed to be in centimeters, not in millimeters. So I'm just going to do a quick conversion because that's pretty easy. 730 millimeters, 73 centimeters. You just have to move the decimal place one spot. Okay, so that's about 3/4 of a meter. That's what this column would measure. Okay, if I went into the lab and actually measured that, 73 centimeters of mercury. Okay, so that ratio has to equal my density ratio. Now, on the problem, I'm told that the density of mercury is 13.6 grams per cubic centimeter. And I think we're told that the density of water is 1.0. If you're not told that, hopefully you know it by now, okay? So this ratio is 13.6. All right, so if I work that out, 13.6 is what I get, right? And of course here the units would cancel. So what this ratio or factor tells me, I know 13.6 tells me that this ratio has to also be 13.6 because they're equivalent, right? So to do the math and figure this out then, to figure my H2O, my height of my liquid water column, I would need to do the 73 centimeters multiplied by this 13.6 ratio, all right, to solve for my height of my liquid water. And if you do that on my calculator, I get 992.8 centimeters of liquid water. 992.8. Now if I'm worried about sig figs, I might go with 990 on that, I suppose, okay, if I'm considering sig figs. And of course, the reason why that is because if we look back to where we started, we had 2 sig figs here, so our answer should also have 2, which now it does, okay? Now the thing is that this is what my column of water would read if I'm doing this experiment for liquid water. It would be 990 centimeters, okay? That would exert the same pressure or indicate the same pressure as 73 centimeters of liquid mercury. But remember, this 73 centimeters, that's about 3/4 of a meter, so that's a substantial difference. Right? We're talking a couple feet there, right? What is this distance in water, in a column of water, okay? Well, centi is 10 to the minus 2. So if I want to convert this to meters, I could do that. Wouldn't it be about 9.9 meters? Wow, that's almost 10 meters. That's like around a first down in football, basically, okay? If you want to think about it as an approximate distance. Around 30 feet or so in that vicinity. So if I was going to make a barometer out of liquid water, I would need to have a room with a really, really tall roof. I mean, I need a special facility just to house this 10-meter long column of water. So we use mercury in barometers because it's a lot more convenient, because it's very, very dense. It's a very, very dense liquid. And as a result, the column will be, manageable. All right, so that's problem 5-6.